Welcome to the NMN video tutorials on CSP technologies, Block 6, Unit 12, Data Uncertainty Analysis. My name is Nicole Janot and I have been working on CSP technologies at DLR for more than 6 years. My main fields of work are parabolic trough and component performance testing, test evaluation, and performance simulation. After a short introduction to the motivation, this unit covers the basic concept of uncertainty, different types of uncertainty, their combination to uncertainty budgets for derived quantities, as well as the meaning of expanded uncertainty. The theory will be illustrated using the example of direct normal irradiance measurements, and the findings will be summarized at the end. Let's have a look at why the evaluation of a measurement's uncertainty should be an integral part of any test data evaluation. Most importantly, the uncertainty of a test result determines its significance. What does this mean? A measurement reading or result as such is essentially a random guess of the measurand. It does not contain any information on how likely the value is to represent the actual measurand. In other words, you do not know how good or bad the value is unless you know the width of the associated uncertainty band. Consequently, reliable values of uncertainty are absolutely necessary for the assessment and comparison of test results. Carrying out a full uncertainty analysis requires a thorough knowledge of a measurement process. If this knowledge already exists, the uncertainty analysis is a mere review of the measurement process and data acquisition. Thus, it constitutes a good opportunity to detect possible errors or inconsistencies. Should the knowledge be incomplete, the uncertainty analysis is likely to reveal existing gaps so that they can be filled in. In any case, uncertainty analysis is a means of reviewing a measurement as well as a good sensitization to the measurement process itself. Performance test results are typically derived from various measurements like temperatures, flow rates, irradiance, and so on. So there's a certain functional relationship between the actual measurements and the measurement quantity that is determined. In this context, it is instructive to determine the contributions of individual measurements to the overall uncertainty. This way, the most relevant influences identified. With the help of such sensitivity data, the overall uncertainty can be reduced most effectively. Altogether, we have seen that analyzing a measurement's uncertainty is essential for establishing a basis for valid comparison of test results. Let's have a closer look at the concept of uncertainty. The uncertainty of a measurement is defined as a parameter associated with the result of a measurement that characterizes the dispersion of the values that could reasonably be attributed to the measurand. In other words, what is the interval about the measured value that is likely to encompass the true value with a certain probability? As no measurement process, no equipment is perfect, it goes without saying that every measurement result is fraught with uncertainty. In the past, measurement uncertainty has been considered in terms of error. The concept of error implies that there is a true value relative to which the magnitude of error can be quantified. In practice, however, such true values will never be known. Uncertainty, on the other hand, refers to the measured value. In terms of the mathematics involved, the two concepts are very similar and still found in literature. However, the concept of uncertainty is preferred today. The term error rather tends to be associated with actual errors like misinterpretation of readings, wrong wiring, or confusion of signals. Such errors are virtually impossible to detect and correct once the test has been completed, and therefore extra effort should be spent to prevent them. The general rules for expressing and evaluating measurement uncertainty are set in the Guide to the Expression of Uncertainty in Measurement with so-called GUM. GUM is the standard by the International Standards Organization and will be the basis for the following. In order to qualify the uncertainty of a measurement process or data collected, the terms of accuracy and precision are commonly used. Although in colloquial language these terms might seem interchangeable, they are not synonymous but rather describe two different aspects of uncertainty. The accuracy of a measurement system refers to the degree of closeness of the measurement of a quantity to the actual true reference value. or in other words, how far the measurements might potentially be off the target. In terms of probability of frequency distribution of measured data, this translates as an offset of the mean value of the distribution with respect to the actual value. This is illustrated in the graphic on the top right. The precision of a measurement system, in contrast, describes the degree to which repeated measurements under unchanged conditions show the same results. This is also referred to as reproducibility or repeatability, which is expressed as variance or standard deviation of a probability density characteristic. The lower the variance, the higher the precision of the measurement. The fact that these two are independent characteristics of a measurement is illustrated in the graphic on the bottom right using the examples of targets with the reference value at the center. The first shows a result that is neither accurate nor precise. The points are off the center and are scattered considerably. The target to the right shows good accuracy with the points equally distributed about the center, but still low precision with considerable scattering. For the one on the bottom left, the inverse is true. The reproducibility, thus precision, is good, but they are considerably off the target, thus inaccurate but precise. The one on the bottom right represents what we are aiming at for high-quality testing, high accuracy and precision. At the same time as clarifying the meaning of accuracy and precision, this example indicates that they are not equally easy to detect from measurement data. While precision can be deduced from the data and its reproducibility itself, an assessment of accuracy requires the knowledge of the actual target value, which is hardly available. In practice, the accuracy of measurements can only be assessed by comparison to reference instruments of higher accuracy. The standard full expression of a measurement result consists of the best estimate of its value, marked x bar, and the standard uncertainty. In many cases, the best available estimate of a randomly distributed quantity x, for which n independent observations xk have been obtained under the same conditions of measurement, is the arithmetic mean or average x of the n observations. The standard uncertainty u of x is the positive square root of the variance of x. How exactly this is calculated will be shown in the following. In terms of uncertainty, GUM distinguishes two types of contributions, the so-called types A and B. Type A encompasses all uncertainty effects that become manifest as variation of the measured values, such as signal noise or general reproducibility. These are evaluated by means of statistical analysis. The experimental standard deviation of a series is calculated from the formula stated, and the experimental standard deviation of the mean is derived. The standard uncertainty resulting from a type A analysis corresponds to the experimental standard deviation of the mean and the square root of the variance. Type B uncertainty effects encompass all uncertainty effects that are not purely statistical, thus all additional knowledge of the measurement process. To this end, various sources of information can be relevant. The instruments themselves are characterized by their calibration certificates. Manufacturers' specifications can also be instructive. If available, experience from previous measurement series could be taken into account, as well as any additional experience or knowledge, such as results of instrument characterization, for example. In order to be able to include all this information in the calculation of the resulting measurement uncertainty, the individual uncertainty effects need to be modeled. Depending on the kind of information, different modeling approaches can be applied. For uncertainty specified as multiples of standard deviation, normal distributions are suitable. This mainly applies to previously evaluated uncertainties, for example resulting from instrument calibration. In other cases, limiting maximum values of uncertainty might be specified, for which rectangular distributions are most suitable. Selecting the correct modeling approach and assumptions requires a little experience and is decisive for Type B results. Let's have a look at an example of a Type B uncertainty evaluation. Say the uncertainty limits were stated for one particular measurand and no further information on the distribution was given. In this case, we can but assume that within the given limits, all values of the measurand are equally probable. This means that the distribution is uniform. Thus, a rectangular distribution would be most suitable to model the given information. For the calculation of the standard deviation of such rectangular distribution, the half-width is decisive. The value of a corresponds to the half-width of the limiting interval. On this basis, the standard deviation is calculated as half-width divided by the square root of 3. In the case of a temperature measurement with the best estimate of 100 degrees centigrade and plus minus 4K as limiting uncertainty values, this would result in a standard deviation of about 2.3K. Thus, the measurement would read 100 degrees centigrade plus minus 2.3K. Similarly to the formerly used propagation of error, there is a propagation of uncertainty that is more commonly called determination of combined uncertainty. As indicated by the name, the combined uncertainty encompasses all uncertainty contributions so that the resulting effect on the target value of a measurement can be quantified. The combination of uncertainty effects can be calculated on several levels of an uncertainty analysis. One particular measurement, like temperature or flow rate for example, can be influenced by several uncertainty effects, so that the calculation of combined uncertainty makes sense on this level. Or the target value of a measurement, like useful heat or thermal efficiency, as in the case of performance testing, is calculated from several measurements, which also necessitates an evaluation of combined standard uncertainty. In any of the mentioned cases, a functional relationship linking the individual uncertainty effects and the target value is required. With the help of this functional relationship and the standard uncertainties of the contributing measurements, the combined standard uncertainty of the target value is calculated. Essentially, this is achieved by adding up the product of the squared sensitivity and the square of the standard uncertainty for all effects or contributing measurements as expressed by the formula on the right. It adds up all uncertainties of contributing quantities weighted according to how the measurement result varies with changes in these quantities. This slightly simplified formula is only valid for uncorrelated input quantities. Should there be a considerable correlation between input parameters, further terms are need to be included. In the context of uncertainty evaluation, standard always refers to a coverage of 1 sigma. A normal distribution of the resulting uncertainty is assumed, so that the value corresponds to covering 68.2% of all possible outcomes. So let's summarize what we have seen so far. Various contributions of the two types of uncertainties, A and B, can be relevant for measurement. In a first step, these are modeled individually and then combined to express the uncertainty of individual measurements. Subsequently, the combined uncertainty of the target quantity of the measurement is calculated from them. As illustrated, the standard combined uncertainty encompasses a fraction of 68.2% of all results that can reasonably be associated with the measurement. For many applications, a wider interval covering a larger fraction of possible results is required. This can be achieved using a so-called expanded uncertainty. The expanded uncertainty is calculated by multiplying the standard combined uncertainty by the coverage factor k. The value of k is derived from normal probability density distributions after choosing the desired coverage probability as illustrated in the graphical representation on the bottom. For values of k of 1, 2, and 3, the coverage probability amounts to 68.2, 95.4, and 99.6%. K equal to 2, or a coverage of 95.4%, is a common choice. This represents a good trade-off between a considerable coverage and limited informative value towards details of the distribution. Let's have a look at an exemplary uncertainty analysis. Say we were measuring the direct normal irradiance using a particular instrument, the CHP1 manufactured by Kip & Zone. What would be the sources of uncertainty to be considered? First of all, there are a number of possible uncertainty contributions which result from the instrument itself. Its repeatability, how much would the readings fluctuate? Its precision, how far might the readings be off the target value due to particular effects of the measurement process or instrument characteristics. And the calibration, what type of reference was the instrument compared to and what was the calibration procedure. Before the analog readings become available as measurement data, they are converted into digital values and logged. Consequently, uncertainty of these processes also needs to be taken into account. For this particular application, all effects considered can be assumed to be uncorrelated. In the first step, the type A uncertainty shall be investigated. To this end, we further assume that measurements taken during a short period of time under clear sky conditions essentially correspond to repeated measurements of a constant quantity. The data recorded and illustrated in the diagram results in a mean value of 929.6 watts per meter square, which shall be used as the best estimate in the following. Looking at the characteristic of the DNI measurement on the right, we note that there are only minor fluctuations of the data. This is confirmed by the calculation of the value of the standard deviation of the data. It amounts to 0.4 watts per meter square and represents the type A contribution to the combined uncertainty. As for the analysis of the type B uncertainty, the instrument specifications are often a good starting point. They state characteristic contributing uncertainty effects for the particular kind of instrument. In this case, a number of effects are specified. The zero offset describes the maximum deviation of the instrument signal at zero irradiance from the expected value of 0. The non-stability characterizes to what extent readings may deviate with time since the last calibration. The non-linearity quantifies possible deviations of the readings from the target value due to the fact that the sensitivity of the instrument is not strictly constant across the entire measurement range. Temperature dependence describes the deviation of instrument sensitivity with growing deviation of operation and calibration temperatures. All instruments of a series are to comply with the limiting values stated in the instrument specifications. Individual instruments might outperform the general specifications, but unless they are characterized individually, this worst-case scenario will be adapted. The calibration uncertainty is a characteristic of individual instruments and calibration procedures. For pyrheliometers and most other instruments, it becomes manifest as the uncertainty of the instrument sensitivity, which indicates the particular relevance of this contribution. When carrying out an uncertainty analysis, one of the main challenges lies in accounting for all relevant uncertainty contributions and realistically estimating their contributions in order to neither under nor overestimate the combined uncertainty. Additional tests and experience are very beneficial at this stage. In the case of additional effects that could be relevant but will not be considered within the scope of this example are instrument soiling and tracking accuracy, for example. Further type B uncertainty contributions are likely to arise from the data acquisition system. For the loggers used in the example, a general system uncertainty of 0.3% of the measured value and of 2 digits can be expected. This results from the analog to digital conversion and the limits of the discretization of the display. In this case, an uncertainty of 2 digits means that not only the last digit is uncertain because of rounding, but that it can actually vary by 2 digits. For a value of 4, for example, the actual value of the last digit could be 2, 3, 4, 5, or 6. Besides, AD converters are usually relatively sensitive to operation temperature. Therefore, an additional uncertainty contribution of 0.005% of the measured value per degree temperature difference of the instrument temperature to the calibration temperature needs to be accounted for. If the instrument temperature is not known, the ambient temperature can be used as an approximation. In the present case, there's a temperature difference of 4 K, which results in 0.02% of the measured value. Having considered a rather large number of individual contributing uncertainty effects, these are then combined to the uncertainty budget. Most importantly, this uncertainty budget requires a functional relationship, a formula that unites all contributing effects and relates them to the desired measurement quantity. In the present case, this is relatively straightforward as the pyrheliometer directly measures the desired direct normal irradiance. Therefore, the reading DNI measure and all other effects simply need to be added up. For a better overview, all previously discussed uncertainty contributions are listed in the table. The first column states their names or IDs, the second the uncertainty specified. According to the type of uncertainty and the specification, the chosen distributions are either normal or rectangular. A normal distribution is applied for the type A uncertainty, characterizing the repeatability and the uncertainty of the calibration factor. This is in accordance with the uncertainty stated in the calibration certificate. All other uncertainty contributions are assumed to be rectangular, as only limiting uncertainties are specified. Each uncertainty is associated with a best estimate and a standard uncertainty stated in column 4 and 6. In accordance with the functional relationship, all best estimates, except that of the type A evaluation, are set to 0. As a consequence of the simple functional relationship, the sensitivities of all contributing effects equal to 1, and the standard uncertainties are calculated using the specified uncertainty and the distribution. The combined standard uncertainty calculated from these values amounts to about 5 watts per meter square. The so-called uncertainty index, the relative uncertainty contributions of individual effects, are easiest to judge in form of a pie chart. On the basis of this visualization, the uncertainty of the calibration, non-stability, and non-linearity can be identified as determinant factors for the uncertainty budget of this particular DNI measurement. Other contributions, like those of the data acquisition, offset, or temperature dependence, have comparatively little impact on the overall uncertainty. Due to the number of measurements involved, the evaluation of an uncertainty budget for performance tests is more complex than that of the exemplary DNI measurement. As illustrated by the schematic, uncertainties are first evaluated at the level of measurements, then combined to intermediate quantities like temperature difference or solar power, and further combined until the derived target quantity like efficiency or useful heat is obtained. In the course of this unit, we have seen why uncertainty analysis is part and parcel of any measurement activity. It provides the basis for an objective comparison of test results and is thus particularly relevant for performance testing. The theoretical basis, general approach, and mathematical rules for the expression and evaluation of uncertainty in measurement are summarized in GUM in form of a standard. The exemplary evaluation of the uncertainty budget of the DNI measurement illustrates that a good uncertainty analysis requires a sound understanding of the measurement process and equipment. And maybe one more note, for the sake of transparency and traceability of uncertainty analysis, it is very important to always state the complete input information, functional relationships, and modeling approaches used. This brings us to the end of this lecture on data uncertainty analysis. Thank you very much for your attention.